Assalamualaikum, Doctor, and greetings to my friend and my fellow members. So, our group today is doing experiment 6, which is torsion of bar. So, for the introduction, we have what is torque. Torque is a measure of the force that can cause an object to rotate about axis, just as force is what causes an object to accelerate in linear kinematics. Torque also is what causes an object to acquire angular acceleration. Other words, torque also a measure of the effectiveness of such a force that consists of the product of the force and the perpendicular distance from the line of action of the force to the axis of rotation. Next is angle of twist. Angle of twist can be defined as the angular deformation in an object due to a couple of twisting torques. So the unit of angle of twist we using in this experiment is radian. Next is modulus of rigidity, which is G, is a shear modulus of rigidity as the ratio of the shear stress to shear strain in a rigid material experiencing an external force, shear or tangential. So the value of modulus varies from different materials depend on the table. So this is our illustration of how what is torsion. Next is the application of torque in our daily life. So we have three example, and for the objective to investigate the relationship between torque and the angle of twist of a circular cross section bars. Also to determine the modulus of rigidity of the material used. So our scope is load that was used between 5 to 25 Newton increment by 5. Rod that we use for the experiment are three solid rod, which is steel rod, copper rod, and aluminum rod. Length of the pointer set used for the experiment was 200 mm and 400 mm. And the radius of the pulley used for this experiment is 115 mm. That's all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Batrisha binti Abdurrahim, and I will explain about theory of working principles in this experiment. So first of all, when a bar is subjected to a torque, it twists, creating a shear strain in the material. The angle of twist is proportional to the applied torque, with the constant of proportionality called torsional rigidity. The torsional rigidity depends on the bar's geometry and material properties, defined by the modulus of rigidity, also called shear modulus, which is G, which measures the material resistance to shearing. So in figure 1 here, we have two different rods that show the difference between tension and torsion. Alright, for this slide, as you guys can see, we have two different formula there, which is top formula to calculate G, bottom formula to calculate V, which is angle of twist. But it's actually came from the same formula. So let me explain first. What are the elements that we use in this formula? Firstly, we have V, which is angle of twist, either in degree or radian. L for length of shaft. T, torque that can be exerted on the shaft. I will explain more about T in the next slide. J for polar moment of inertia. We use pi r to the power of 4 divided by 2 to find the value of J, because in this experiment we only use solid rods instead of hollow rods, because when we have hollow rods, we will use another formula. Okay, so that's why we use pi r to the power of 4 divided by 2. And lastly, we have G, modulus of rigidity of the certain material. So as you guys know, we only use steel, copper, and aluminium rod in this experiment. So those three rods have different values of G and it's fixed. So we don't need to calculate the values of G of each rod anymore. So we have 79.3 gigapascal for steel, 45 gigapascal for copper, and 27 gigapascal for aluminium. So in figure 2, shows the illustration for torsion. And first figure, we have illustration of how to find D and F, and second figure to find, um, not to find, how to identify the value of T, L, and also R. As I mentioned before in the previous slides, T is the torque that can be exerted on the shaft. So the formula of T is force multiplied by distance. So the force applied to the shaft is the different loads that we use in this experiment, which is 5 Newton, 10 Newton, 15 Newton until 25 Newton. And D distance, which is the perpendicular distance from center of shaft to the point of force on this of apparatus. So for different loads and different distance, we will have different torque.
For experimental setup, we've got our rope, which is quite difficult to see by our naked eye, but the rope will be attached to our pulley and our weight hanger, which is the second weight hanger. The weight hanger is used to place our weight. The third is clamp tightener. The clamp tightener will be used to tighten the metal rods that will soon be attached to the pulley. The fourth is metal rods. So for this experiment, we've got three types of metal rods, which is steel, copper, and aluminium. The fifth is our weight. So our weight will be used by the increment of 5 newtons. And lastly, we've got our clamp. Our clamp will clamp our metal rods to the initial point and to our pulley, which will later be experimented and will show us the angle of twist for all three metal rods.
The first step for the methodology is to clamp the metal rod at both ends and make sure the length of the pointer set used for the experiment was 200 millimeter and 400 millimeter, as you can see from the diagram. For step 2, we hang the load hanger, attach it to the end of the rope. Next, number 3, we adjust the pointer so it is pointing on the 0 on the rotational scale. We can also call it zeroing into the scale. Next, number 3, we adjust the pointer so it is after the step number 3, we can proceed to step number 4, which is placing the weight on the weight hanger. And then what is responding is the pointer that is going to tell you about the angle. So we record the angle from the rotational scale after that. All right. So we can proceed to number 6, which is repeat the data collection by adding the weight by 5 Newton each data, starting from 5 Newton to 25 Newton. Now for number 7, we repeat the experiment using different metal rods.
So for the next part is safety procedure. So we have three safety procedure in our experiment. We separate into three category, which is weight handling, secure clamping, and proper outfit. So for weight handling, when adding or removing weights from the load hanger, do so carefully and incrementally because dropping weight can cause sudden jerks leading to equipment instability or personal injury, which is leg injury, etc. etc. Ensure that the weights are added or removed slowly to maintain balance and control in the experiment. Next is secure clamping. Ensure that each solid rod, which is steel, aluminum, and copper, is clamped securely before applying any load. A poorly clamped rod can slip or eject under torsion, causing potential injuries or damage to the apparatus. Be careful with the hand when clamping to avoid injuries. Lastly, proper outfit. Wear lab coat and covered shoes to secure safety when conducting the experiment. This can also prevent injury and incident such as falling load on the legs from happen in the experiment area.
So for table 1, we've got aluminium rod, we've got hanger load in Newton, torque in Newton times millimeter, and angle of twist, which we've divided over two sets of data, which is in radians and in degree. So during the experiment, we'll be using the degree, and as for the calculation, we'll be using gradients. So the rod radius for aluminum rod is 3.125 millimeter, and to calculate the top, which is force times rod's radius. For table 2, we've got copper rod, and as same as the table 1, we've got the hanger load and torque and angle of twist. So the radius for copper rod is 3.05 millimeter. For the third table, we've got steel rods data, similar to table 1 and table 2. The only thing that is different, which is the rod radius, which is 2.485. And since the radius is different, so the torque will also be different. And the angle of twist will also be different. So for our first graphs part, we've got angle of twist against torque for aluminum rod. So the data that I have shown, the table, is directly from table 1, which is correlated with the aluminum rods data over 200 millimeter and 400 millimeter. So for 200 millimeter, we've got the graph plotted, and the crucial part, which is the gradient that we'll be using later for our calculation for finding the rigidity of the modulus, is 0.005 for the first part, and the second part is 0.0022. So for the second graph part, we've got angle of twist against torque, but this time for copper rod. So similarly, we've taken the data from table 2, which is correlated with copper rod's data, and the gradient for over 200 millimeter is 0.0023, and for over 400 millimeter, the radius is 0.0022. And the final graph part, which is angle of twist against torque, but for this time, which is steel rod, the data that we'll be using is from table 3, correlated with steel rod's data. And as for the length of steel rod over 200 millimeter, we've got the gradient 0.0042, and for over 400 millimeter, we've got 0.0025. For discussion, we'll be discussing about finding the polar moment of inertia and modulus of rigidity for all three metals with their corresponding length of rods, which is over 200 millimeter and over 400 millimeter. So you will notice that the polar moment of inertia will be same for our both lengths for each individual rods, because for finding the polar moment of inertia, we'll be using the formula pi times the diameter of the specific rod to the power of 4 divided by 32. So notice that there isn't any relation for gradient to be used, or any other calculation or any other data. So the data for polar moment of inertia for 200 millimeter and 400 millimeter for both lengths will always be same, since there isn't any length used or any other data used. So back to our data, the diameter of aluminum rod is 6.25, and the gradient that we've already obtained from the first graph part, which is 0.005, the polar moment of inertia is 149.8028. The length of rod L is 200 millimeter. And finally, the modulus of rigidity G that we can obtain by using the formula, which is G is equal to L, length of rod, over M, gradient, times by polar moment of inertia J. So here we've got 267.0177. And for the second part, for aluminium length over 400 millimeter, we've got the gradient 0.0022, the diameter, which is same, the polar moment of inertia, which is same that I've mentioned earlier. The length of rod, only the length of rod will be different, which is 400 millimeter, and that length of rod will affect the modulus of rigidity. So the modulus of rigidity for aluminium over 400 millimeter length is 1213.7168. And the average modulus of rigidity for aluminium rod, which we could obtain by adding both the modulus of rigidity and divide by 2, which we will get to 740.3672. For our second part, we've got the copper rod's polar moment of inertia, modulus of rigidity. So the copper rod's diameter is 6.15 millimeter. The gradient for copper rod over 200 millimeter is 0.0023. The length of rod L, which we just mentioned now, 200 millimeter, and the modulus of rigidity G that will be obtained from the formula G is equal to L over mg. So L is the length of rod, m is the gradient, and J is polar moment of inertia. So the modulus of rigidity that we've obtained is 619.1584. So for copper rod over length 400 millimeter, the gradient is 0.0022. The diameter, which is same, the polar moment of inertia also same. Only the length of rod, which is different. That will also alternate our modulus of rigidity, which is 1294.6040. And the average modulus of rigidity for our copper rod now is 956.8812. And for our third part, we've got the steel rod over 200 millimeter and steel rod over 400 millimeter. The gradient for 200 millimeter is 0.0042. The diameter of steel rod is 4.97 millimeter. The polar moment of inertia J is 59.8998. The length of rod L is 200 millimeter, and the modulus of rigidity G is 794.9783. And as for the length of steel rod over 400 millimeter, the gradient is 0.0025, diameter is same, polar moment of inertia is same, the length of rod is 400 millimeter, and the modulus of rigidity is 2671. 0.1270. So for the average modulus of rigidity for the copper rod is supposed to be steel rod. There's a slight correction. So the average modulus of rigidity for steel rod is 1733.0526. Finally, we've got table 4, which is the overall data that we've obtained for this experiment. There we've got the type of rod, all three rods that we've used for the experiment, their corresponding length that we've calculated the data from, all their corresponding diameter, their polar moment of inertia, their gradient, their modulus of rigidity, and their average modulus of rigidity. So that's all from me for the discussion part. Thank you. For reference, we've got Talk Definition and Meaning by Merriam-Webster. What is the angle of twist by B. Juice? The definition, unit, and formula for shear modulus of rigidity, and our textbook, Mechanics of Materials, done by J.M. Timoshenko. And for the same reference, we've got Engineering Toolbox, Models of Rigidity, Shear Models of Material, retrieved November 14, 2024 from our corresponding website. And finally, our Wikipedia contributors. So that's all from me from the reference part. Thank you.